Okay, so we'll call this this is circular motion, but it's some advanced circular motion if you want. Not too advanced, but we'll call it circular motion part 2. Okay, so we arrived at this last time. First, we derived a formula that looked like this. Okay, and then we said, well, if this is true, and we multiply both sides by m. Okay, so mac and mv squared. Ma is force, but it's a special kind of force. That's the centripetal force, and that equals mv squared over r. Okay, so any type of force that's causing an object to follow a circular path is considered a centripetal force. All right? So it's not an absolute force, it's a class of forces that cause circular motion. And it can be gravity, friction, tension in a rope. It could even be a normal force if you're going around a wall or something like that. And I'm just going to put etc. A lot of different things can cause circular motion. The key to defining it all as being centripetal force is the fact that that force is always angled at 90 degrees to the current velocity of the object, and it always points towards the center of the circle. Okay? So whatever happens to be doing this, whether it's, a little model airplane tied to a rope in the center or your car turning around a corner, or whatever, the force is angled towards the center, and that causes the velocity to constantly change direction. All right? The acceleration comes from the direction change, not from a change in magnitude. All right? All right, so we're just going to expand on this a little bit, and we're going to look at the geometry of a circle quickly. That is not a circle. Let's see if I can make a circle here to start us off. Okay, perfect. All right, so let's remember what we know about a circle. Circle's a radius. And if you want to find the distance around a circle, okay, you're going to use 2 times this magic number pi times r. 2 pi r. All right? Now let's imagine that you are moving around a circle, or you have an object that's zipping around a circle. Okay? The time it takes to go once around the circle is designated as t, which is called the period. So the period equals time for 1 revolution. And period is just designated as a big T. All right. Now, if you look in this formula, you see that there's a velocity in there, right? Okay. Now, the thing is, oftentimes, it's pretty hard to directly measure the velocity of something going around a circle. But if something happens to be going around and around in a circle, it's much easier to find the time, and maybe you know what the radius of that circle. So what we're going to do is we're going to recall that velocity, or speed in this case, because we're interested in the magnitude, is going to be equal to the distance around this circle divided by the period. So then we can say it should be equal to 2 pi r over t. Do you agree with that? Okay. And we know this from before. So what we're going to say then is we should be able to substitute this guy in for velocity. Okay? Velocity. So that would look like this. M 2 pi r over t, all of that squared over r. All right? Well, that looks like a big mess, but let's see what we can do with that. So we should be able to square everything inside of here, right? So m 2 squared is 4, pi squared, r squared, divided by t squared, okay, all over r. And then we do one more thing, where it now becomes this. So we're dividing by t squared and r squared, right? So we can just do this. Oh, sorry, r, t squared and r. And then we're going to have a cancellation here, one of those, and we end up with this. The centripetal force can also be said to be equal to m 4 pi squared r all over t squared. So you oftentimes see that formula given to you like this. One can be derived from the other, okay? And then using the same logic that we used before, okay, we can divide an m out of both sides, and you can also get this. So that's centripetal acceleration by dividing out mass from both sides, okay?